In this video, I will explain hypothesis testing and test of means. What is hypothesis? We have theories or statements about many different things, especially when we compare two different groups based on any parameter of the population, and we have to check that, see if that comparison or the statement we make is true or not. Examples include a percentage of the population, for example, College of Business students attending the next Huskers game. It should be based on some information, some opinions. Implementing the new rewards plan will increase productivity. Is that true? Well, we have to verify that. After implementing the plan, we have to compare the performance after and before the plan and see if there is a significant change in performance. Total hours of study is positively related to the letter grade of a student. We have a sample, we have to verify that based on the total hours of study and the grades, compare and see if that's true. Many other examples exist, including those that everybody knows about. There's enough evidence for backing up those statements, like smoking tobacco is related to lung cancer. We call these statements alternative hypotheses. There's always a null hypothesis against alternative hypothesis. What we call hypothesis testing is a test of what we think might be true or our premise about any topic or result of experiment against something we already have in hand, we know about it. So there's always a null hypothesis versus our alternative hypothesis. Now, null hypothesis in this example says that College of Business students at the next Huskers home game will be at most 25%. The notation is that we say H naught represent that by M less than or equal to 25% or 0.25. Alternative hypothesis is the negation of what we have, null hypothesis. More than 25% of COB students will attend next Huskers home game. A similar notation, we just have a different direction, H sub A for alternative. In any statistical test, we try to provide evidence against the null hypothesis, hoping that we can reject the null hypothesis. If we can't reject the null hypothesis, then we fail to do so. Or we may have an equation in mind. Similar to the previous null hypothesis, we estimate that the COB students in the next game will be 25%. M equals 25. Alternative hypothesis is the negation. The percentage could be more than 25% or less than that, but anyway, it is not equal. So a hypothesis is a research question, and that question needs to be investigated. When comparing two or more samples or groups, null hypothesis always states that there is no difference between the parameter value we're interested in and the base value or the range. It could be any of those examples: game attendance, level of emissions, for example, for the cars we're compared to the standard, grades earned by students, or increasing productivity. So in hypothesis testing, the research question is always stated as alternative hypothesis, and research effort is always on the null hypothesis. We always try to reject the null hypothesis by finding some evidence against the null hypothesis. By rejecting the null hypothesis, we establish the alternative hypothesis, find some support for that, and failing to reject the null hypothesis means that there's no evidence for validity of alternative hypothesis. It's not feasible or even possible to test the entire population, so we take samples. We test these samples to find some evidence for rejecting the null hypothesis and then make an inference for the population. So there should be a statistical test for rejecting the null hypothesis. Stating hypothesis about population mean takes one of the following forms. Alternative hypothesis says the mean of the population is less than a given number. Let's say that's about the average age of the people in an area, and that's 55 years. M is 55. Null hypothesis states that average is not less than 55, could be more than 55 or equal to. We call this a one-tailed test. It's a lower tail because the alternative hypothesis is pointing towards the lower end of the population. It states that the average is less than a given number. The other type of one-tailed test is upper-tailed test, when we state in alternative hypothesis that the mean of the population is more than m, more than the given number. In this case, null hypothesis is that mean is less than or equal to m. When we don't know the direction, the number could be more than or less than, we have a two-tailed test. In this case, alternative hypothesis says that mean of the population is not equal to a given number, and null hypothesis says it is equal to the given number. And we can apply these hypothesis statements to the mean of any population, being about the people, about the revenue, sales, or any other factor. So one example to explain on is this hypothesis. Null hypothesis says that teaching business analytics in a computer lab is not more effective than a traditional classroom using pen, paper, and calculator. Alternative hypothesis says that teaching business analytics in a computer lab is more effective comparing to the traditional settings. This is a one-tailed test because we say that the computer lab setting is more effective. How do we measure that? By the average grade of the students. So this will be a test of means. So we may have one of these two situations. Based on null hypothesis, teaching in computer lab is not more effective. Observe some difference between the computer lab and traditional class outcome, but we don't call this big enough to be a significant difference. The difference could be due to sampling error, different group of students. It's not showing a consistently better result from the computer lab. But then there should be a limit. How much of difference should be there to call this a significant difference? We consider a critical region 5% or 1%. Let's say with 5% to the right tail of the distribution when we have distribution of grades for traditional class. If we do have the distribution of the computer lab grades as the green distribution, the mean of that distribution is not quite there into the critical region. It's not showing significant difference. The red line, the red distribution, we can observe that the mean of that distribution is within the critical region, far enough from the mean of the traditional class to call this a significant difference. So the objective of the test of means is to show that the difference of the means of the two groups we're comparing is big enough to fall within the critical region, and that's 5% upper end of the distribution. If we do fail to reject a null hypothesis, it means that the data is inconclusive. It doesn't mean that the null hypothesis is true. Maybe with another sampling, another test, we can find out that there is a significant difference between the two. Now, we'll look at the significance level, critical region, and p-value. Alpha level, which determines the critical region, is set by the researcher, 1% or 5%. For example, if you want to have 95% confidence on your results, you consider 5% into the critical region. If you want to have 99% confidence, you will consider alpha at 1%. And what is the p-value? This is important to understand what's the p-value which you will observe for every single test. Not just test of means, all tests. When we have 5% in the upper tail, when we project the distribution of the results of the computer lab, that mean falls somewhere in critical region. The portion of the critical region that is separated to the right, which is, of course, less than 5%, that area is the p-value of the test. So the smaller the p-value, the more significant the results. So a very small p-value, that means the mean of the sample is too far away from the mean of the base or the traditional class. So that p-value, the smaller, the better, the stronger support for rejecting the null hypothesis. So the p-value is our evidence against the null hypothesis. In this example, we can see that the critical region on the right is smaller than the p-value area. Our p-value area is larger than the critical region of 5%. So p-value here, for example, could be 8% or 10%. In this case, when p-value is larger than that 5% or 1%, depending on the significance level you selected, we fail to reject the null hypothesis. The means of two groups are too close to call it a significant difference. So think of p-values as probability of rejecting the null hypothesis while it is true. Null hypothesis says no difference, and we will reject it and be wrong. So the smaller that probability, the better. There are a group of tests for comparing the means. If you do have two independent random samples, just for two groups, there are parametric variables and normal distribution. These are the assumptions of these tests. We can use z-test if the population standard deviation is known. And if we don't know the population standard deviation, we have to use t-test. There are also non-parametric tests for two independent random samples, Wilcoxon and Whitney. These are the tests used for two samples. If we have more than two independent random samples and our data is parametric with some assumptions that I will explain later, we use analysis of variance or ANOVA. There's a non-parametric test we'll look at, Kruskal Wallis test, when the data is not parametric or the assumptions of ANOVA are not met. So analysis of variance tests the equality of three or more sample means. Null hypothesis says that these means are basically equal. There's no significant difference among them. Alternative hypothesis says that the means are not equal, at least one of those means is significantly different than the others. ANOVA is based on some important assumptions. Dependent variable or the response is normally distributed in all samples, so we have to check for normal distribution. And we do have homogeneity of variances or homoscedasticity. The variances of samples are not significantly different, so we have to check for that assumption too. And observations must be independent. These are the assumptions of ANOVA. So graphically showing, if you have three samples and the means of those samples are not significantly different, we can call them samples from the same population. There's no significant difference. The differences of the means we observe are due to the sampling error. Or we may have at least one of those samples significantly different than the others. There's not much of overlap between that sample and the others, so that we can call that part of a difference population. In this case, we will reject the null hypothesis. So how we do test this? And the reason we call this test analysis of variance. We compare the variances in two different ways. We calculate the variance of all these samples together in two different ways and compare these two values. If they all belong to the same population, there's no significant difference among them, then these two values should not be very different. In case of observing a lot of difference between these two values, which is through f-test, then we conclude that there is a significant difference between the means. We compare the sum of squares between the groups. Calculating sum of squares between the groups means that we have an overall mean and we measure the deviation of the mean of each one of those groups and this overall mean. So each one of those samples or groups are represented by its mean, and we can calculate the sum of square deviations relative to the overall mean. This is one way of calculating the variance. The other way, we call this sum of squares within the groups, is that we calculate the variance by measuring the deviation of each one of those sample observations by the mean of the same sample. And then pool the variance, pool all these variances together. And this is the second way of calculating the sum of the squares. So stating this as formulas, we're trying to find out if significant difference in means leads to significant difference in variance calculations. So comparing these two between the groups and within the groups using these two formulas. And then the ratio, we call this the F value. We do have standard F test. The ratio of mean squares between the groups over mean squares within the groups. There are standard F tables. We can use this ratio and degree of freedom to find out if this is a significant difference between those three or more groups. If the F value we obtain is more than the F critical that we obtain for the groups through the standard table, that means there's a significant difference between the groups. There's an Excel formula as well for calculating that F value, the F critical in Excel, and graphically showing F distribution. If we do have F value that exceeds the F critical, then we will reject the null hypothesis. There are other tests, non-parametric tests, when we do not have the assumptions of ANOVA met. Ordinal scale of measurement used here for comparing, for example, in cases of the height or weight of the people, if we do rank order them, people understand them better comparing to stating them as inches or pounds. There might be many different reasons for ranking. Ranks are easier to understand, or original measurements may violate assumptions of a test. For example, the distributions are not normal, or we do not have the homoscedasticity, which is required for t-test and ANOVA, or our experiment has inconclusive outcomes for some observations. We don't know what the exact number could be, but they could be ranked relative to the others. So in Wilcoxon signed rank test, we compare the differences between two treatments or two independent samples. Absolute value of difference between the pairs of scores will be ranked ascendingly, and then based on those ranks, we compare the proportion of high and low ranks among the overall ranking. If there's no difference between the two groups, then the members of two groups or two observations should be distributed all over. Kruskal Wallis test, which is for 3 or more groups, is an alternative to ANOVA when the assumptions of ANOVA are not met. There is no requirement for numerical data. We can rank order the individual observations. There is no need for homoscedasticity of the samples, and degrees of freedom are defined by the number of treatments or populations. The details of these tests are explained through the examples I will use for the class. There are several tests for homogeneity of variance or homoscedasticity. We look at the Levene's test, since it does not need normal distribution of the samples. The null hypothesis of this test is that the variances of all those samples we're looking at are about the same. They are not significantly different. Alternative hypothesis is that we do observe significant difference among the variances. At least one of them will be significantly different. So any significant result, which is a very small p-value of this test, indicates that the variances are significantly different. And this is one of the cases where ANOVA is not a valid test. Another test available in JMP is Bartlett test, which is used when there's a strong evidence that the parameter of estimate, the response we are looking at, has a normal distribution. So to summarize, when we do test of means, we are comparing the means of measured parameters for groups. We want to find out if they are significantly different or not. We have to go through questions. Do we have more than two groups? If it's no, which is we have only two groups, then we have to ask if population variance is known. If the population variance is not known, then we can use t-test, given that the distribution is normal. Do we have equal variances and normal distribution? If we do have that, then z-test or Welch's t-test can be used. Well, the first question, if the answer is yes, if we do have more than two groups, then Our first candidate test is ANOVA because parametric tests are always better than non-parametric. They have more power of detection of the differences. Then first we have to check for the assumptions of ANOVA. Test of variances. If we do have homoscedasticity, we do tests of unequal variances, and more importantly, look at the Levene test, and also check for normal distribution. All samples must be normal. If we do have both assumptions met, then we use ANOVA. Otherwise, if we miss one of those assumptions, we use Kruskal Wallis test.